What makes the best coffee cup? Well, you have your stainless steel cups, which are durable and keep the coffee warm for an hour. You have your stoneware cups that are thicker, porcelain, china mugs that can keep the heat in longer. You have insulated tumblers with double walls and lids, and this prevents a lot of heat loss and spills. And then you have your thermos or vacuum insulated mugs, and this is where it can keep your coffee hot for hours. So, if we're thinking about the coffee cup, what is happening there? Well, it's all about insulation, and that's what we're going to talk about today when we're thinking about heat loss. So in today's lesson, we're going to be calculating energy changes using water. So the study design dot points are using specific heat capacity of water to approximate the quantity of heat energy released during combustion of known mass, and this is with fuel or food. The principles of solution calorimetry, including determination of the calibration factor and consideration of the heat effects, the heat loss effects, and analysis of temperature time graphs obtained during solution chemistry. So when we're thinking about the heat combustion of fuels and food, what we actually need to look at is the specific heat capacity of water, because we can actually use this to transfer the energy from that food or fuel to the water, and therefore we can actually do a calculation with how much energy is being transferred. So when we're looking at the specific heat capacity, it's to estimate the energy released in a combustion reaction, and that's for fuel or food. So if you remember back in Unit 2, the specific heat capacity is the energy required to increase the temperature of a specified quantity, usually 1 gram per 1 gram by 1 degrees. So the specific heat capacity of water is 4.18 joules per grams per degrees, and this is found in your data book. So water has a relatively high specific heat capacity, and this is why it's very useful when we're doing these types of calculations, because that means we can actually heat the water up, do the calculations without it vaporizing. So if you actually have a look at the specific heat capacity of other common substances, you can see water is up here, 4.18, and you can see other liquids are almost half that. So you have glycerine and ethanol, almost half that, and then you even have lower ones when you go to sand, copper, and lead. So water is very, very useful because we can actually use this to calculate the energy of fuel or food. So when we're calculating the specific heat capacity, we are going to use a formula. Now there is a lesson link here. So Unit 2, 9A, Thermal Properties of Water. This is where we first spoke about the specific heat capacity of water. And we first used this formula shown. So this is exactly the same, nothing has changed. So we can determine the heat energy absorbed by a given mass of water using this equation. So we have E, which stands for energy, and this is measured in joules, equals the mass, and like all mass calculations in chemistry, it's in grams. The specific heat capacity is given the symbol C, and this is given to us in the data book. And then we have the temperature change, and this is in degrees. So this is the change of temperature from the beginning to the end. Okay, so make sure you're looking at that temperature change. So this is the same formula, and so the same type of calculations, but we're going to have a look at that. So when we're thinking about the heat combustion in experimental sense, there are some steps that we need to follow. So this flow chart helps identify each of these steps when we're trying to calculate the heat of combustion in an experiment. So the first thing we need to do is we need to measure the volume of water. Now, it doesn't really matter what the volume of water is. It will probably depend on the beaker or the glassware that you're using. But say if we say 100 mils, we would measure and place it in. It says metal can, but this can be different depending on what type of apparatus you have. You can do it in beakers and things like that, but you do need to take into account heat loss when we're using glassware instead of metal with lids and all that. We're going to talk about that further. And then we're going to measure the initial temperature of the water. So before anything happens, what is the temperature of the water? And this needs to be done every single time because that temperature of the water will change, especially if you're doing repeat trials. The next step is to measure the mass of the spirit burner and the fuel. Okay, so how much fuel you're actually burning. Or if you're doing food, you would need to measure the mass of the food and the holder that you're holding the food in. The reason why it's important to measure the holder of the food or the spirit burner itself is because you would have to then measure that at the end. You won't be able to necessarily take the leftover food or the leftover fuel and put that just on the balance itself, okay? So you'll need to still weigh the holder and take that away. Then you're going to light the burner or the food, so this is actually on fire, and heat the water, stirring continuously. Now, sometimes there are some nice nifty little things that can stir the water by itself, depending on, again, what apparatus you're using. If you don't have it, you can stir it yourself, but obviously be aware that you do have an open flame underneath it. Have a set amount of time that you're going to do this for. Now, this could be 2 minutes or 5 minutes, or if you want to continue it to the flame goes out and can no longer be relit. It depends on what your experiment is and what the design of your experiment is. But so after a certain amount of time, extinguish the burner and record the highest temperature that was reached by the water. So it's important that you are measuring the temperature throughout, because you might see the temperature start to drop after the flame gets smaller as there's less food or less fuel to burn. And the last step is to measure the mass of the burner and the remainder of the fuel or food, and this would deduce the amount of fuel or food that was actually burnt and produce that energy into the water. So that's the general steps. Some things to think about is that we are assuming that all the energy from the fuel or the food is going into the water. Now, we know that that's actually not the case. In reality, lots of heat is actually lost to the surrounding environment, and it can also be absorbed by the can or the glassware or other things that you have around. So in reality, lots of heat is lost, but this will actually give us a calculation of what should be transferred and then identify what actually has been transferred, so we can get that theoretical versus calculated. So when we think about calorimetry, we think about the energy released from a reaction. So calorimetry is actually an experimental method, and it's similar to the method that we looked at before. That is a type of calorimetry method. But with calorimetry, there is normally specific equipment that we can actually use to calculate the energy being released from a reaction. So the simplest form of calorimetry, the heat energy released by a chemical reaction can be transferred to water in a separate container. So that's what we looked at. Now, there are types of calorimetry where you can actually, like this one given to us in the image here, where it's all closed and everything is kept, all the heat is kept in, so there's less heat loss. But the most simplest one is the one that we've already looked at. So the quantity of energy transferred can be calculated from the increase of temperature in a calorimeter. And so that's what we have done in the past. So in those simple versions of calorimeters, we need to consider the heat loss that's happening to the environment, because this does change our results a lot. So when heat energy from the burning of food or fuel, so that's happening down here in the spirit burner or the apparatus that you would hold the food, the substance is lit on fire. Now, not all of this energy here is going into the water, all right? Lots of it is, because the fire is heating that water. But because this is all open in this particular setting, this is all open, heat's being lost out from the flame, as you can see here, as being lost from the beaker. There's nothing insulating that beaker at all, like it's not covered by anything, so heat can come out from the glass. And as there is nothing on top here, or we're going to assume there's nothing on top, heat is actually also lost from the top here, so as you can see. So what happens when nothing is put in place to prevent that heat loss? Well, a lower change of temperature occurs. And so this means that the calculated energy is actually less than what it is. So that means it's not giving us the actual energy efficiency that's occurring with that particular fuel or that particular food. So how can we prevent this? So the first thing we could do is put a lid on the container that we're using. So no matter what this is. So even if you only have a glass beaker, you can put a lid on it to ensure that no heat loss is lost from the top. We can also insulate the beaker. So if we don't have a particular calorimeter that's already insulated, we can surround the beaker by something. Obviously make sure it's not flammable. So aluminium foil is a really good one. It's just going to insulate that water. And then the other thing is you can actually place insulation around the burning food, but obviously make sure that there is enough oxygen to continue that combustion reaction. So that could just be like just putting something around it so there's no air coming in that's moving the flame, and so that means the flame is directly going in there and it's less heat loss as much as possible. So when we're looking at an actual calorimeter, we can actually determine how much heat loss is actually occurring with that particular piece of equipment. And this is really important for us to be able to determine the actual energy release from a fuel or a food. So when we're thinking about the heat change, we normally use the formula, this energy, this with the specific heat capacity, but unless all that energy is going, that's going to be inaccurate. So what we're going to do first is we're actually going to calculate what's known as the calibration factor. And this is by putting in a known amount of energy into the calorimeter. So that means we can actually see how much heat loss is occurring. So what we need to do is, so this is measured in joules first of all. So the calibration factor is measured in joules per degrees. And then once this is known, we can then use this to continue our experiment and know that the calorimeter is calibrated, and then use that calibration factor for future calculations to take that into account, any heat loss that's occurring, making our results more accurate. So there are two types of ways to calculate the calibration factor. So the first one is an electrical way. So a calorimeter can be calculated using an electric heater. So this is when you actually have a specific calorimeter that has this function. This won't work with just a beaker or anything like that. So this needs to be a proper piece of equipment that has this function. And what you can do is you can use electricity to be able to supply, to heat that electrical heater by a certain amount of volts, amps, and by a certain amount of time. And then by using all this, we can actually calculate the calibration factor. So how much energy is supplied and how much energy is actually being released and kept inside. So when we're looking at that, this is the formula we're going to use. So energy in joules. So we have the voltage, and this will all be given to us in the question, or if you're doing the experiment itself, you would record this. The current, so the amps, and the time, and that needs to be in seconds. So be careful of your units here. It's important that they're at these particular units. You can simplify it down to Q equals V times I times T. Now, once you have that, you can then use that by doing the Q that we found here divided by the temperature change. And so this is actually taking into account how much heat loss is occurring. So it's important that you're measuring the temperature alongside the volts, amps, and seconds. So the second type of way to calculate the calibration factor is actually using a chemical reaction with a known energy. So this would be a fuel that's known, or an enthalpy that's known very well, and it's very consistent, doesn't break down, doesn't react with other things. So conduct an exothermic reaction with a known enthalpy and a known quantity of fuel. And then we're going to measure the change of water, so the temperature change that's occurring. Then we're going to use stoichiometry to calculate the theoretical amount of energy. So how much energy should actually be supplied to the calorimeter. Then by doing that, we can actually calculate the calibration factor by dividing that by the temperature change. So similar to before, we calculate the energy, how much energy should be supplied, but then dividing it by how much the temperature does actually change. So after we calculate the calibration factor in either one of those methods, well, what do we do with it? Well, we actually need to use that when we continue on our experiment. So here are some steps on how we use the calibration factor in an experiment. So we will determine the calibration factor, either method, chemical or electrical. And then once you've done that, you need to conduct this unknown reaction in the same calorimeter. Cannot stress that enough. There is no point of running a whole calibration factor, calculating that up, and then using a different calorimeter, because then it's pointless. So same calorimeter needs to be used. If you're doing it in different sessions of your class, make sure that it's labeled so you do get the same one the next time. Measure the temperature change of water, so you would do that in every step that you do, and calculate the energy released in joules using the formula. And then Q can be calculated using the enthalpy change of the reaction per mole per gram that we did in the previous step. So the same way that we calculated that before, we're just taking into account the calibration factor. So let's have a go at a question. A bomb calorimeter was calibrated by passing 1.5 amps through an electric heater for 50.5 seconds at a potential difference of 6.05 volts. The temperature of the water the calorimeter was initially measured at 18.05 degrees and rose to 19.38 degrees during calibration. Determine the calibration factor of the calorimeter. So this is the electrical method. We've been given the amps here, the seconds here, and the volts. So no conversions are required. It's already given us in the units that we need. So we're going to use this formula. So the volts, 6.05 times by the amps, 1.50 times by the seconds. Put all that in a calculator and we get 458 joules. So don't forget this energy is in joules. Then we're going to calculate the temperature change. So we have the final temperature, 19.38, take away the initial temperature, 18.05. And that gives us a temperature change of 1.33 degrees. To calculate the calibration factor, we're going to do the energy, which is found in step 1, divided by the temperature change found in step 2. So that is 458 divided by 1.33. And that gives us 344 joules per degrees Celsius. So this question is worth 2 marks. So the first mark is calculating the energy released by the calorimeter. So that's using the volts, amps, and time. And the second mark is calculating the calibration factor by working out your temperature difference and dividing that by the energy from step 1. All right, let's have a go at another question. A bomb calorimeter was calibrated by a complete combustion of 1.00 grams of benzoic acid. And we've given some information for benzoic acid. So we've been given the molar mass and we've also been given the enthalpy of benzoic acid. The temperature of the water in the calorimeter rose from 17.50 to 21.67 during calibration. Determine the calibration factor. So because we've been given the enthalpy change of this particular chemical, this is a chemical calibration factor example. So the first thing that we're going to do is we're actually going to calculate the mole of benzoic acid. As we've been given the mass, we're going to use the mass over molar mass formula, and we've been given the molar mass of benzoic acid as well, so it makes it nice and easy. So we have 1.000 grams divided by 122 given to us in the question, and that gives us 0.008197 mole. The second step is to calculate the energy, and this is using the mole that we just calculated in step 1 and timesing it by the enthalpy that was given to us in the question. Now, we don't need to worry about the negative sign here because that's just indicating it's an exothermic reaction. We just need the actual energy. So the mole is 0.008197 times by 3,227, and that gives us 26.45 kilojoules. Note that it's in kilojoules here, and that's because our enthalpy is in kilojoules per mole. It's important that you do follow the units here. In the previous question, it was in joules because the formula that we calculated gave the energy in joules. This is in kilojoules because the information that we've been given is in kilojoules. The next thing is to calculate the temperature difference. So we have the final, which is 21.67, take away 17.50, and that gives us 4.17 degrees Celsius. The last step is to calculate the calibration factor. So we have the energy, and this was calculated in step 2 divided by the temperature change calculated in step 3. So 26.45 divided by 4.17, and it gives us 6.34 kilojoules per degrees. So this one is worth 3 marks because there is a bit more involved here. So we have calculate the mole of benzoic acid is the first mark using the mass over molar mass. Calculate the thermal energy released by benzoic acid, so that's using your enthalpy change given to you in the question. And then calculating the calibration factor using the energy divided by the temperature change. So when we're looking at energy changes, just looking at solutions, so different types of reactions in solutions, we can use what's known as a solution calorimeter. And these are very, very similar to the other calorimeters that we've looked at, but they're actually quite simple. So generally they're made from a polystyrene foam cup and it has a lid. So these two things are really important in terms of insulation. So polystyrene is a really well-known insulator and the lid obviously stops the heat from escaping from the top. So it's the polystyrene prevents the transfer of heat to the surroundings of the calorimeter. So it doesn't absorb on the sides either. So that's like when you have heat coming from a hot beverage coming from a polystyrene cup, you actually don't feel hot. So the cup protects that. So therefore it just keeps everything inside where it needs to be measured. The reaction carried out in the calorimeter is accurately known volume of water, and we're still calculating the initial and final temperatures, and it's measured and recorded, and the amount of the reactants is also measured and recorded. So when do we use this? Well, we look at this when we're looking at the energy change in the lab, specifically with solutions. So lots of acid-base reactions are done in a solution calorimetry experiment. Also when we're looking at dissolving solids in water. So these are the most common ones, but generally we need to have solutions reacting and looking at that energy change. So there are some limitations when we're looking at the polystyrene. So the temperature change is lower than if it does absorb. So if it's been used quite a few times, it can start to absorb that. So if it's quite an old calorimeter, solution calorimeter, it can start to absorb some of the energy. And so therefore the calculated value released or absorbed will be lower. Solution calorimeters can not be used to measure energy content of food because you need to have it in solution to be able to do that. So you can't actually light the food on fire in a solution calorimeter because it will burn the polystyrene and you also need to have access to oxygen to run that combustion reaction. So food cannot be calculated, it needs to be the other way that we've looked at. So this is only for particular reactions that are in solution form. So when we're measuring the temperature change occurring in calorimetry, it's not always as simple as just calculating the beginning to the end because we can have differences depending on how well we have insulated our reaction. So ideally, this is what we want our reaction to look like if we were to graph it. So we want it to begin, we have a nice linear drop, and then we have a plateau. Now that's not always the way. So generally, this is what our graphs will look like. Okay, so we do have a nice flat beginning, and it does go up linear, but then you can see kind of going up and down depending on what's happening, and you can see that some of the heat is being lost as well. So it's not really plateauing out nice and level as it should be, and this would be due to the insulation of the container that we have. So because of this, we need to take into account this heat loss. So if we can't do the calibration factor as done before, we would use these temperature time graphs to be able to extrapolate what should actually be occurring. So the actual temperature difference here. We're looking at that. We're going to look at the temperature change and we plot the graph as shown. The temperature against time, and then we can actually extrapolate. So we would actually use where the temperature started to rise, so that's here, and then we use a line of best fit going from our last point and draw it up to that point where the temperature started to rise. And this is where our temperature change would occur. So from here, so the 20 degrees to 5 or 24.1 degrees, that's where our temperature change would occur. So by extrapolating it, we get a more accurate depiction of actually what occurred. So to summarize, specific heat capacity is a substance that measures the quantity of energy, usually in joules, and this is the amount of energy required to increase the substance of 1 gram by 1 degrees. We use this formula here when we're calculating with specific heat capacity to calculate the energy, and we need the mass in grams and the temperature change. Solution calorimetry can be used to determine the energy change, generally in the lab when we're using acid-base reactions or dissolving substances in water, and this is what that setup looks like. We have 2 ways to calculate the calibration factor. So we have using an electrical way, so that's this one here, when you have your volts, amps, and time in seconds. And then you have your chemical way using the number of mole. The calibration factor is calculated the same way using either energy calculation. So the energy from either the thermal released by volts, amps and time, or by the number of mole being reacted, divided by the temperature change. What's coming up next? We have energy from fuels and food. I will see you then. Bye-bye.